Today we'll have Brett Nasserden, who will tell us about simple homogeneous ACM bundles on partial flag varieties.
Thank you. So, by trying to describe a class of vector bundles on a smooth projective variety that are kind of nice and that are cohomologically.
Thank you. It was on, but it was on mute. You were right. It was power was on, but voice was not on. Can everyone see green? Is that okay? Let's go to this. It's the nice angel chalk. So I've got a smooth projective variety, and it's also going to be and coming with an embedding in projective space. So I've got X and then OX of 1. So this is now a very ample line bundle. Maybe, okay, well, let's just say it's over C. So kind of the main object that we're going to be discussing today is ACM bundles. So, and ACM vector bundle on X. So this means arithmetically Cohen-Macaulay. So it's going to be a vector bundle E such that HI X E of t is 0 for all I between 1 and the dimension of X minus 1. And all T in Z. So E of t is what happens when you take E, you twist it by OX of t here. And so it depends on my choice of embedding, right? So to get the different twists. So an ACM vector bundle is one that has no middle cohomology. So maybe here, here. Right, so this is dimension of X minus 1. So it's a vector bundle with no middle cohomology. So this is an ACM vector bundle. Maybe the first motivating example would be X is projective space. And then I have the usual O of 1 on projective space. So the only ACM bundles are direct sums of line bundles. So this is by Horrocks. If I don't know, this is a maroon, if it walks like a duck, then it is a duck. If it looks cohomologically like a direct sum of line bundles on projective space, then it is a direct sum of line bundles on projective space. Yeah. You said something about a duck once, and I don't remember once. All I remember is that there was maroon in the duck, and so I just wanted to put it out there on YouTube. So this is maybe the first motivating example. And so then you could ask, okay, what about other projective varieties? And maybe the idea is you test the complexity of X through the category of ACM bundles on X. So here we're seeing, or from this perspective, okay, maybe X itself does not have, from this perspective, projective space doesn't have such complicated geometry. And so all we have is essentially just this one direct sums of this ACM bundle, up to twist, describe all of them. And you can maybe break this up into two cases, maybe say finite, wild. So here, finitely many composable ACM bundles. And then wild, maybe arbitrarily large families of indecomposable ACM bundles. So this is maybe the perspective that if we have a lot of ACM bundles on there that are indecomposable, we can't break them up into direct sums of line bundles. And then maybe this is this wild type, and maybe in the middle I could have something tame, or maybe you have a discrete family of ACM bundles, something like this here. Okay, so this is the idea. And part of the reason why this might be nice is so in the finite case, there's a complete classification. So you've got projective space, smooth quadric hypersurfaces, you have a smooth rational curve. So, okay, it depends on the embedding. So you embed, P1 inside of some projective space. Smooth, let's say cubic scroll in P4. So this is the first Hertzsprung surface, F1. And then, okay, the Veronese surface. And that's the whole list of all in the finite case. So in the finite case, okay, that these are the options. So it's a small list. It's a small list. Yeah.
So first Hertzsprung surface is ACM when you embed it in P4, and it's not if you embed it in a higher projective space. Like, maybe I'll ask you this later, but I'm curious about like the bundles which break this. Like, what's a bundle that's ACM on F1 when it's embedded in P4, but not in higher embeddings.
Well, it's saying with this embedding that there is only finitely many. And the other embeddings, there would be more.
Right.
There would be more because you're twisting by something else now. Maybe I'll just say something here. Maybe in this middle tame case. So maybe just a step beyond this. Where do we have things like this? An elliptic curve. Smooth quartic scrolls in P5. Okay, maybe I'll even allow like a reducible tree of rational curves. So and then maybe there's a few sporadic others. The list is slightly longer. So there's again a classification here. And essentially everything else is yeah. 100% not. 100% not. So okay, so he said, okay, finite MCM types. So these are coming with an embedding. So I can look at the homogeneous coordinate ring of these things. And so now if I take one of these ACM vector bundles, maybe I'll just write it here. I was going to say this, but let's just do it now. So imagine that I do this. So I hear, okay, so I've got X, and so now I've got SX. This is the I've got the homogeneous coordinate ring, E ACM. So ACM is like the geometric side. If I'm trying to do more commutative algebra, what do? I look at okay, what am I doing here? K in Z. Yeah. Thank you. So I look at this and I get a module over the homogeneous coordinate ring. I get a module over the homogeneous coordinate ring. And then ACM is corresponding to this being an MCM module and vice versa. So that was one of the original reasons for studying this, was that ACM vector bundles, give you these MCM modules over the homogeneous coordinate ring. So that's where the study from the commutative algebra side came from. Yeah.
P1 cross P1. But it has the quadrant 2, and I think that's the only one. No. Yeah, because I can take O, and if I twist it around, I can get to things that have middle components.
Wait, I think it's that, but we're taking, so we've got the smooth quadric hypersurface embedded as a hypersurface in Pn. So what are you trying to do? Yeah.
Okay, I guess at some point maybe I would like to ask what are the finitely many ACM models like that?
I think it's what is it? It's gonna be like O of 1, 0 and O of 0, 1, I think. With respect to that embedding. Like with the 1, 1 embedding. Maybe I'm forgetting, but I believe that is the case. If you took a different embedding, then you don't get, it's no longer finite. Right, so it depends on the embedding. It depends on the embedding. So the same thing it really depends on the embedding. That makes sense? Yeah, interrupt me at any time. Yeah, go ahead. Here, right here. Okay, so you take the homogeneous coordinate ring, right? So that again, so it depends on the embedding. Now I take my vector bundle, I form this, and this becomes a module over the homogeneous coordinate ring. And then if you're an ACM bundle, this means that this is a maximal Macaulay module for SX, for the homogeneous coordinate. Yeah.
So I guess I'm also wondering, so in the case of any curve, what do you mean by ACM in that case? Like, are you just saying that the class of indecomposable bundles is finite, or?
So you have your curve, but it's embedded in some space. Yeah.
So I guess that, but if it's a curve, it has no middle cohomology. Right? So you're taking cohomology for X, or do you mean to like?
Well, what do you mean the curve?
Well, the condition there for all I between 1 and X minus 1 becomes vacuous. So that's what I'm asking. Like for curves, the ACM condition is vacuous. So
yeah, for curves, the
dimension is 1.
For curves, the thank you. Yeah, it should be, this should be, I guess, so we're saying that this should be, we're saying this is in here. And so maybe we should put this as n minus 1. Thank you. Okay, so here was one reason to care about it, and I made this list, and everything else essentially that is not on this list is of wild wild type. So maybe I'll just say that here. Yeah, so there is also a complete classification for team. And this is relatively recent. And so this was by in 2019, okay, building on. Okay. Eisenbud. Hartshorn. Herzog. Who else did I leave? Dross. Et cetera. So this kind of classification program kind of ended 6 years ago. And And so we know that most things are wild, but it's still interesting to try and produce these infinite families, or classify now as best we can what do the ACM bundles look like. I'll just remark that, part of the perspective on this is that, the kind of the category of all vector bundles on a smooth projective variety is very big. And it's kind of hard to get your hands on. So how do you kind of cut it down? You can put stability conditions on it, like, a la Mumford and, through GIT, things like this. And then maybe an alternative approach really emphasized by, Costa and some others is instead you put some cohomological conditions on them. And so one of them is this ACM condition. I'll note that so who here has ever heard of a Ulrich bundle? Has anyone ever heard this term? So an Ulrich bundle is a special ACM bundle. So it's a subfamily of all ACM bundles that has kind of, had an intense amount of interest going back to, I guess, Eisenbud and Schreier in 1983, where they realized that if your variety has an Ulrich bundle, which is a special ACM bundle, what does Ulrich mean? It means that it's this plus the top cohomology also vanishes. That's one way of phrasing it. Then you can get an explicit equation, or it makes it easier to get explicit equations for the Cayley-Chow form of your variety, if you know what that is, which is saying you take your variety and then you look at all the planes in a specific Grassmannian and intersect it. This gives you this Cayley-Chow form, and it was an open and still challenging problem to find an explicit way of representing equations for that. It's somehow easier if you have an Ulrich bundle. So this special ACM bundles. And maybe I'll just note that if you like this MCM approach here, then the Ulrich bundles are the maximally generated MCM bundles. So that also has an interpretation here. So this is maybe the reason why we care about these things. Any further questions right now at this moment? So we know that everything is I told you that most things are wild. So what we would like to be able to do is still find some interesting classes of vector bundles that are ACM, and then maybe use them to start building more and more. And so I'm going to focus now on a specific case. So I'm going to go to Grassmannians. And so I'm going to ask the question. So it's too big of a question to say, what are the ACM bundles on a Grassmannian? Okay, maybe that's too big because it's going to be wild. But although in fact, when they first started doing this in 2016, they didn't know it was necessarily wild yet. And this was a case where they showed it was wild. And so how can we get our hands on here? So here, so what I'm saying is that I've got, let's say, the Grassmannian of let's say we'll use K-planes in Pn. And then I've got an action of GLN now on this Strassmannian. And so now I want vector bundles that are equivariant with respect to this action, which means that the structure map should be a GLN equivariant map. And the idea is that this is something that is much more manageable, because we basically know exactly we know exactly what they are. And then maybe this is a hint. I'll remind you again that so here, this is saying that well, okay, maybe I'll say it in a second. So we want to use this. So I have my tautological exact sequence here. So let's just write it like this. So let's say that I'll call this G. And I'm choosing this just because this is just the notational choices that are used in the literature, where this as rank K+1 and this as rank N minus K. So really, in this notation, the dual of this is the tautological bundle. And then the dual of this is the tautological quotient bundle. So admittedly, this is a little bit confusing, but this is the choice that we do. So here we're on the Grassmannian, and now we have this tautological exact sequence here. Yeah. Which one is the tangent bundle? Well, the tangent bundles can be the tensor of the two of them. Yeah. Yeah, it's going to be the tensor of the two of them. Yeah, yeah.
So the left one is okay, yeah. Which side does the tangent of your 0 space?
Yeah.
Yes. Ah.
So we have these things here, and the point is that all of the homogeneous or the equivariant vector bundles on here, the indecomposable ones, can be built out of these two things here. So we'll fix alpha, which is going to be beta and gamma. We'll take beta, gamma, partitions of length K+1. So this is beta and N minus K. So this is gamma. And then all of the equivariant vector bundles are coming from, well, the indecomposable ones are coming from taking Schur functors of these things. So then let's take sigma beta of Q tensored with sigma gamma of S dual. It's a partition of length k plus 1. So it's got k plus 1 elements. Gamma has n minus k elements.
Okay.
Yeah, yes. Okay, sorry. And these bundles here are the equivariant vector bundles, the GLV equivariant vector bundles on my Grassmannian. So these are the push forward of some line bundle from the flag variety, as we said in the learning seminar talk. And the point is that if I want to ask the question, is this an ACM bundle? I have to be able to compute the cohomology. How do I compute the cohomology of something like this? I have to use Borel plot of it. Oh, I did. Yeah, well, let's write it the way Borel will. So this is this computes the cohomology. So the idea was that, okay, we have these things. I've got this class of vector bundles, which is kind of nice in some way, but it's extra nice because I can actually compute the cohomology of these things. And so I actually have a hope of actually determining which ones satisfy this condition here. So maybe let's just remind ourselves about what is in this setting, in the Grassmannian setting, what is the theorem saying? So I have this. I've got rho, because this is an annoyance because I am switching kind of notations from the learning seminar talk, because it's going to change what my vector rho is. But here, okay. We've got this, and I'm just making this choice to be consistent with, if you ever look at this paper, this is what we end up using here. So we've indexed it one extra. Okay, then one. Hmm? Yeah. And then what am I saying? What am I saying here? I've said, okay. So I want to compute this. What do I do? One. Let's just say it like this. Alpha plus rho is a repeated entry, no cohomology. B otherwise, how did I write this? Yeah, G decrease. So what do? You compute this. This is this. If there's repeated entry, no cohomology. Otherwise, you find the permutation that takes alpha plus rho, turns it into something non-decreasing, and then you have a unique cohomology group in the length of that permutation. So in particular, for all of these bundles, there is exactly one non-zero cohomology group. There's precisely one non-zero cohomology group at most,
Or can you elaborate, what's the notation, like the sum raised to, I guess, is a partition, like,
So which one?
what is this sum?
Oh, no, this is the Schur functor
Oh, it's sure.
at this thing here. Right, associated to this partition here. So this is increasing, and now you subtract off this thing here, so it's still increasing, it's still some partition, and so you get this. Okay, you have to be able to deal with negatives things in here, because I never said anything there, but that corresponds to twisting by some line bundle. And there's a formalism that tells you how to deal with this. But essentially what you do is you twist up, so you get something positive, you do this, and then you twist back.
So, and ACM
No, they may or may not be ACM vector bundles. This is just computing the cohomology. And we want to now use this to determine when this is true. Right, so that is the idea. That is the idea. Any questions here? Sir, what was that?
Like in the learning center now, we need to apply some permutations until we found one that has that. This seems to be missing some property, or instance.
Yeah. So the idea here is that if you kind of, in this case, if you go through Bott's algorithm there, so the thing that goes wrong is there being a repeated entry, then you keep shuffling them with the bullet until you would get them side by side, and then you would get that bullet fixes it, and then you would be in this case. And then otherwise, the obstruction to be able to be doing that is that there is not a repeated entry here. And so now what you have a list of numbers, none of them repeated. So that means I can then take this and move it into, so it becomes non-decreasing. And then that is and then that's the bullet operation that you end up using. Yeah. No, we just need this one here, non-decreasing. Because if this was all non-decreasing and then I subtracted off this thing here, which is already counting down, then it's still going to be non-decreasing. Yeah, so that's just, yeah. That makes sense? That makes sense? Okay, and so now the game is to just work through this and to just see what happens. So what are the types of things that you do? So I'm allowed to do twists. So I'm going to say it's initialized if H0 of this is non-zero. So I like that because it's kind of that what I'm saying is we know that this thing has that these vector bundles have cohomology in at most in that 1 degree. So the idea is I want to twist it so then I have it in H0. And let's say, what do I want to say? And I can further demand that this is 0. Okay, and strictly speaking, because here I'm twisting by OG1. Coming from the Pluker embedding. So you can say exactly in this framework, what does twisting correspond to? We won't get into it, but so we can always assume this here. And now we want some way to organize all of this data. And so we're going to do, it was originally done in this case by something called the step matrix. So I'll just define it for you. So a P by Q step matrix PJI such that T J plus 1 I minus T Ji is equal to epsilon j, and Tj I plus 1 minus Tji is equal, okay, I can say gamma I. So the differences between the rows and the columns are all constants here. So if I go and I look at this jth column, then all of these differences are constant, and all of these differences are constant. And so then what do we do? So I have my sigma q tensor sigma gamma SV. So beta this is B1 all the way up to BK plus 1. Gamma is A1 all the way up to AN minus K. And what do you do in this situation? Well, I'm going to define TJI by this funny formula. So it's going to be B K plus 2 minus J minus AI plus I plus J minus 1. So now this is I between 1 and N minus K, J between 1 and K plus 1. And so then maybe the lemma TJI is a step matrix. And I'll just say here that if I had a step matrix of this correct size here, then I recover the ACM bundle that by kind of inverting this formula in a annoying in an annoying kind of way here that I won't write down, but it's 2 lines, one to define the AIs, one to define the BIs. And the point is that the entries of the step matrix end up being able to tell you when you have, okay, maybe I'll say it's initialized. If T11 is equal to 1. And so initialized step matrices under this correspondence, this is 1/2 of it, correspond to the initialized the initialized equivariant vector bundles here. Okay, so this is the step matrix. And then maybe let me just write the theorem. This is initialized. So this is ACM. If and only if I'll set NL to be the number of IJ such that TIJ is equal to L. So it's the number of entries that are equal to L. And the sum, let's say from, I shouldn't say K, L is equal to 1. It'd be 1 plus N of NL minus 1 plus, this just means take the max of this and 0, is equal to N minus K times K plus 1 minus B1 plus N. So you can compute whether something is ACM by writing down this step matrix, which is just this annoying formula, and then checking if this sum is the correct size. So this is cost plus ROA again, 2016. So this is the case of the Grassmannian. And I'll just say that a quick word about the proof, that this formula here is precisely what you end up, is precisely what you need to look at when you stare at Borel-Vaught, or so you stare at this, and then you want to force that this is 0 in this middle cohomological range, and that this formula here having repeated entries is precisely what is showing up as repeated entries in here, and then showing that you have vanishing in this middle range. So that's the idea. So this was done in 2016 to classify ACM bundles on Grassmannians, or classify them, but the equivariant ACM bundles on Grassmannians. And then after doing this, okay, and then you can start building things using this result. You can now build these infinite families of arbitrarily large rank. And so they proved that, an early proof that these Grassmannians were wild, except in, small cases. So in the last 7 minutes, what did we do?
4 minutes.
Oh, we're already 4 minutes. My clock is wrong. Oh, I thought I had an hour. Okay. Sorry. Then, okay, so this was the Grassmannians. If you want to do it for flag varieties. So you take this idea and you try and build a step matrix. Okay, now it's more complicated because you don't have one partition, you've got, R partitions. So instead, you build a block step matrix. Instead of building a block step matrix, and instead of this sum, you end up having to say, okay, I need the entries in my block step matrix to take on some specific collection of values. And this is our result with Dylan, Chadhuri, Ebel, Martin, and myself. Okay, sorry for going over.
All right, let's thank Brett. Any questions for Brett? So you didn't get to mention for your result about your own result? Is it a similar sort of condition that you just have to show that it's ACM if and only if?
Yeah, you
particular-
show that it is ACM if and only if the entries of your block step matrix takes on a specific number of values. Yeah.
Can you actually write down the names of your collaborators? Just so I can also.
I can. Let's see. So Chowdhury, Dillon, and Martin are at Western, and Ebel is now at, I think, University of Pennsylvania.
Other question.
Yeah.
Or you just,
The board you just hit. Going back to what was said earlier that ACM bundles correspond to maximal Cohen-Macaulay modules. So does that translate to I think the definition of maximal Cohen-Macaulay says that they have the maximum kind of
The
what is it,
depth.
depth.
Yeah,
So
yeah.
is that exactly what it translates to then?
Well, what it's translating to is when you then take this this direct sum of the sections, right, and all the twists of DH0, that module over the homogeneous coordinate ring coming from the Pluker embedding, that is now an MCM module.
So then is that the left-hand side, is that actually the depth of that module? Is that...
Oh, that's a good question. I don't know. I don't know if that is the depth of the module.
Okay, then let's save
Yeah.
questions for after and thank Brett again.